So now we know about the Argand diagram, using it to solve problems becomes a very useful tool. Okay? Because remember, we now know that every complex number can be represented not just by a point on the Argand diagram, but more importantly, can be represented as a vector. Now, of course, the advantage of a vector, let's put in our x plus iy, there it is. Vectors can move. So I could pop it down there. It's still the same vector. So it still represents the same complex number. I could put it over there. It is still the same complex number. So this allows us to solve problems rather than algebraically, doing it geometrically. And in fact, that's how maths evolved. Originally, it was all done with geometry, not with algebra. And sometimes, in fact, a lot of times, a geometric solution is going to be far superior to an algebraic solution. Okay, just a reminder, of course, our vector, if ever we're trying to work out what the complex number is, or the vector, head minus tail. So adding and subtracting, well, we've seen this. There's complex number Z1 and complex number Z2. So when they're joined to the origin, it now represents the actual vector Z1, but also the point Z1, because it's head minus tail, Z1 minus 0. But if I want to add them, as we saw, we create our parallelogram. We slide the blue one up there, and we get the position of where Z1 plus Z2 would be. Or we could have gone the blue one plus the red one. We get the same point. The subtraction, that's where we did it head to head. So Z1 minus Z2 would be down there. The black vector is the vector for Z1 minus Z2. And what we saw was actually, I could slide that and it goes to the other diagonal of the parallelogram. Because again, head minus tail. So you must get Z1 minus Z2. The triangular inequality is a very basic idea. If you've got a triangle, then any particular side in the triangle must be shorter than the sum of the other two sides. Because the shortest distance between any 2 points is going to always be a straight line. So in our triangle, gee, it would have been good if I actually labelled them A, B and C, wouldn't it? Pretend they're labelled A, B and C. In a triangle ABC, the side AC will always be less than or equal to AB plus BC. Now, when we're looking at our vectors, I could say, well, I'll pick the side that's representing Z1 plus Z2. So the length of that side must be less than or equal to the length of the Z1 plus the Z2. But now, if I think of that as not sides of a triangle, but it becomes a result for modulus. So the modulus of Z1 plus Z2 must always be less than or equal to the sum of the modulus of Z1 plus the sum of the modulus of Z2. But it's also going to be true about the differences, because you can always play around with it and get a different inequality, which would also be valid. So it would also be greater than Z1 minus Z2. Notice the absolute value around the Z1 minus Z2 is when Z2 is smaller than Z1. And we say the absolute value of that because we're saying, look, we end up with a positive number because the modulus of Z1 plus Z2 has to be positive. So I'm actually interested in the positive result. I really don't care about the negative result. Hence why we have the absolute value on the left-hand side of that one. When would it be equal? Well, that's when we're not talking about a triangle, but we're talking about a straight line. So A, B and C would all lie on the same line. Then you have equality. 1995 HSC. Goodness me. Diagram shows our complex plane, Argand diagram. P and Q, we've got two different complex numbers there. Thus, the length of PQ would be head minus tail, Z minus W. Show that, basically, the triangle inequality. So how would I do it? I'd probably make sure I have the diagram. I'd redraw it in my booklet. And I'd draw in the third side of the triangle. And then I'd say, well, look, the length of OP would be the modulus of Z. The length of OQ is the modulus of W. And length of PQ, modulus of Z minus W. So therefore, by the triangular inequality, this must be true. So I'd do probably something like that. Construct the point R representing Z plus W. What can be said about the quadrilateral? Well, Z plus W must be the other diagonal of the parallelogram. So let's draw in our parallelogram. There it is up there. What can be said about the quadrilateral? At this stage, because we don't know anything about the lengths of the sides, So I think the best we can say is it's a parallelogram, because we know the opposite sides are parallel. Now, if it turns out that the modulus of z minus w is equal to the modulus of z plus w, what could be said about w divided by z? We're saying these two things are equal. So in other words, we're saying the diagonals in our parallelogram are equal. Well, that tells us a bit more about our shape. It's no longer just simply a parallelogram, it's now a rectangle. Now, if it is a rectangle, then I know argument of w minus the argument of z must be pi on 2 or 90 degrees. Because if you look back at the diagram, the difference in those arguments is the vertex of our shape. And if it's a rectangle, that's got to be 90 degrees. Well, using our laws we saw about arguments, that's the same as saying the argument of w over z is pi on 2. So what can be said about w on z? Well, if its argument is always pi on 2, then it's got to be purely imaginary, because it lies on that imaginary axis. Multiplication, we saw this idea. So the lengths we could multiply first, then find the modulus, or find the modulus first, then multiply. But when it came to the arguments, we were adding the arguments. That meant this. So in effect, if you're going to multiply z1 by z2, then z1 is about to get rotated anti-clockwise by the size of theta 2, and the length will get multiplied by the modulus of the other complex number. So here's a problem, and you might think it's unusual for this to be handwritten, but it's a little nod to history, because that diagram was drawn by my maths teacher. So we just keep the history going, you see? So now I've got it, then you've got it, and so on. So if we multiply z1 by cis theta, the vector OA will rotate. So that's what we were just saying. We know then that B is z1 times whatever angle that is, whatever that angle is. The important thing to note about this is multiplication by I, rotation of 90 degrees. It occurs a lot in these problems. So I times z1 would have rotated at 90 degrees. Remember, maybe I'm highlighting it too much. Remember, a vector is head minus tail. All right, let's have a look at this situation. Here's our quadrilateral. We know two of the points. Well, we sort of know two of the points. One is 1, we know that one. The other which is called omega. Let's find all the others. Well, vector DC is equal to vector dA times I. Oh, sorry, I forgot to tell you. That's a square. That's a square. So we know we're rotating at 90 degrees and the length has not changed. So times by I, head minus tail. So the point C minus 1 will equal omega minus 1 times I. This will allow me to find an expression for C. I just make it the subject. So it must be 1 minus I plus I times omega, whatever that happens to be. Okay, that's C. Let's find point B then. Now I've done it this way. I've said, well, to get to point B, I could go from the point A and add on the vector DC. Because I could slide that one up, it would be the same as the vector BA. Okay, well A we know is the point omega. DC, head minus tail, will be the point C minus 1, but we've just worked out an expression for the point C, so we can substitute into that, rearrange things, and we have an expression for B. It'll be minus I plus 1 plus I omega. Of course, I could have done it a different way. I could have said, from the point C, I'm going to add the vector dA. So C, we've got an expression for C. I'm going to add dA, head minus tail, so omega minus 1. Rearrange that, and thank goodness we get the same one. So there are different ways of getting it. In fact, there's another way I could have got the point B. Because I know this is a square, I could have said, I'm going to rotate the vector dA 45 degrees. Because I know diagonals in a square. But I also know the ratio of the sides, because we're creating that 45 degree triangle. So I know the ratio go 1, 1, root 2. So the length of the vector would be multiplied by the square root of 2 as well. So I could multiply the vector dA by the square root of 2 cis pi on 4. All right, well dB, that would be head minus tail, so b minus 1. Square root of 2 cis pi on 4, so that's cos plus I sine. And that'll be times dA, which is omega minus 1. Well, cos of pi on 4, of course, is 1 on root 2, which will cancel with the root 2. Sine pi on 4 is also 1 on root 2, so the same thing will happen there. I've moved the 1 across. Let's rearrange it so we can show it is, in fact, the same thing. So expand those out, group like terms, and yeah, we get the same number. So there's no one right way of doing it, it's just how you're thinking about the problem at the time. 2000, they asked this question. So they gave us a rectangle. And fortunately this time they told us it was a rectangle, so it's not a problem. A is the complex number omega. Okay. What complex number would C be? Now they've told us OC is twice OA, and they've told us this is a rectangle. So it's that rotation idea again. I could get the vector OA, rotate it 90 degrees, but its length I would have to multiply by 2. So, all right, OC then would be OA times 2I. So that's 2I times omega. So there's an expression for C. What complex number corresponds to the point of intersection D of the diagonals OB and AC? Well, we know diagonals in a rectangle bisect. That's something we know about rectangle. Therefore, D must be the midpoint of AC. I mean, it's also the midpoint of OB, but that's not really useful because I don't know what B is yet. So it makes more sense to say it's the midpoint of AC. I know those 2 points now. So the point D would be the point A plus the point C divided by 2 because it's the midpoint. So just our standard midpoint formula. Sub in what we know. So omega plus 2 omega over 2. Well, that's probably good enough for an answer. Wow. I factorised it and made it a half plus I times omega. OBA, equilateral triangle, length 1, makes life easy. OBCD is a square. Find the complex numbers represented by B, D and C. Now here's the interesting thing. Why did they say B, D and C and not B, C and D, which would be more naturally what you would say? They're giving you a subtle hint here on the order to go and find these points. So B, D and C. Well, let's find B. The vector OB would be the vector OA rotated 60 degrees because it's an equilateral triangle. Now I know A because they told me it's length 1 unit, so A must simply be the point 1. So it's 1 times the cis of pi on 3, which is a half plus root 3 on 2I. Okay, D is the next one I'm going for. So OD then would be OB rotated 90 degrees. Or I guess alternatively, I could have said it was OA rotated, what would that be, 150 degrees, wouldn't it? Yeah, I could have done it that way as well. So I times B, we just worked out B, so we get minus root 3 on 2 plus a half I. Now let's work out C. Well, C, if I get the point B and add to it the vector OD, I'll end up at C. So C will equal B plus OD. Well, they said to put it in X plus IY, so let's group those things together. We've got 1 minus root 3 on 2 plus 1 plus root 3 on 2. Right. A and B in our complex plane correspond to Z1 and Z2. We've got a couple of triangles here, and we're told they're right-angled isosceles triangles, although they haven't drawn in the hypotenuse, but fair enough. Part I, explain why P corresponds to the complex number 1 plus I Z1. I know you love these questions where it says explain. In fact, I just didn't bother explaining, I did the maths. Vector AP then would be the vector AO, but notice it would be rotated clockwise, not anti-clockwise. So that would be multiplication by minus I, not I. So P minus A, head minus tail, is equal to minus I times O minus A P minus Z1 is that. Rearranging it, we've got an expression for P. Oh, well, it's going to explain why it's that. Let's factorise it. I think that explains why P is that particular point. Now, on the rotating clockwise, it's not simply negative, it's the argument that's negative. So be careful with that. I can get away with it with I by saying it's minus I, because technically you're multiplying by the cis of minus pi on 2. Well, but because the cosine of pi on 2 is 0, you end up with negative I. If it was a different angle, then you've got to be careful. So it was 30 degrees. Then what you're actually multiplying by is the cis of negative 30. It's not the negative of cis 30. Okay? So it's actually the conjugate you'd be multiplying by. Now, part 3, because there is no part 2, but I'm logically going to do the part 2 that should have been there, because you're going to need it to do part 3, if that makes sense. I'm going to find which one is I'm looking for. Part 3 said let M be the midpoint of PQ. So it makes sense that I have to find Q. I guess that's the logical part 2 that's not there. Find Q. So how do I get Q? Well, the vector QB, how can I get that? Well, I can rotate OB. This time we are going anti-clockwise, so it would be times I. Head minus tail. So we get B minus IB. And B we have somewhere. Oh, it's simply Z2. Okay, so Q is 1 minus I times Z2. Now let's find M. M is the midpoint of P and Q. So the actual points. So sub in those points. I could leave it like that, did I? No, I put it in real and imaginary. Okay, there we go. So Z1 plus Z2 plus Z1 minus Z2I all over 2. So there's the complex number M. The reason I said did I bother putting it into real and imaginary is that does it really matter? Because remember Z1 and Z2 are going to have real and imaginary components anyway. So it's not like that actually is in real and imaginary components. Okay, let's have a quarter of a jolly good fellow.